Hey, good afternoon, everybody, and welcome to Keeping Sustainability Alive from the Inside, Meet the Experts. My name is Pat Keys. I'm the Special Projects Coordinator for the Office of Sustainability, and I'm joined by, these events are always a group effort. I'm joined by my colleague Lisa Williams, who's running the PowerPoint slides, and Eliza Brenman, who is helping out with the Q&A aspect. Okay. And Lisa, I'm having issues seeing the screen, so give me 1 second here.
You're on the agenda slide.
Okay, great, thanks. Okay, so I'd like to introduce our first speaker. The first presentation is From Dust to Us, the Earth Under Construction. We're joined today by Dr. Mordecai-Mark Mac Low, who is the curator and professor in the Department of Astrophysics at the American Museum of Natural History. He's also a research scientist at the Center for Computational Astrophysics at the Flatiron District. We're so happy to have you here. Thanks so much for being here, Mordecai.
You're welcome. Okay, welcome to everybody. I'd just like to acknowledge the funding that this research has gotten from NSF and NASA. My office is on the top stripe to the left at the Hayden Planetarium under normal circumstances. And let's take it away. Next slide, please. Okay, so I grew up in New York City. I went to a public elementary school. In fact, this one, CES 109 in the Bronx. So all our viewers from the Bronx, please give a cheer. And go ahead and start. We pull away from the Bronx and we'll start to see the other boroughs. So as you see your borough, you get to cheer. There's Upper Manhattan, and we're seeing all of the Bronx and Manhattan. And now we're starting to see Queens and Brooklyn, and wait for it, Staten Island. We gotcha. We gotcha. There's Staten Island too. And so now we're going to pull up off away from New York City and indeed off the Earth entirely and fill in the atmosphere with the clouds. And we can see that the Earth is not flat, but round. It's a ball. And over near it is the moon, which is also a round spherical ball illuminated by the sun. So the sun's shining on it from the left, as we'll see. And this is just a round ball being with the sun shining on it. And look, there's the crescent moon. And there's the sun shining on it. This is why you get the phases of the moon, just because you're looking at a sphere that a light is shining on. So now we look at the larger solar system, and you see these colored lines across the screen. Now, what could they be? They're very flat, all in the same plane. And as we tilt up, we see that, oh, those are the orbits of the other planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. They're all lying in the same plane. And this turns out to be a key clue as to how they formed. If we go to Jupiter, the largest of the planets circling the sun, although not the largest planet known because there are many planets in other solar systems that are larger, we see that it also has a mini solar system, if you want, of moons circling it, and they're also in a flat plane, the same plane of the solar system. If we look behind Jupiter, we see this faint band crossing the sky of glowing light. This is the Milky Way, which is hundreds of millions of stars spread out in a flat disk. And in that disk, you can see dark clouds. So that disk is like a pizza, and we're sitting in one of the pepperonis looking out. So we just see the thin direction of the pizza. That's why it's a band rather than a round pie, because we're looking out through it. In that disk, we see these dark regions. Those are not holes in the disk, but rather dark clouds of gas and dust that are blocking the light from the stars behind them. Those clouds, which you can even see with the naked eye in a dark sky site like out in the country, those are where stars and planets form. So if we go to the next slide, we're going to look inside one of those clouds. And now we've switched from what our eyes see to a description. So this is a cloud a couple of light years across that is where I'm showing the yellow bright is the densest parts of the cloud. Go ahead and start the video. And this cloud is collapsing under its own gravity. As the cloud collapses in, densities get higher, pressure gets higher, and so temperature starts to go up. And as it gets denser and denser, the temperature goes up so far that in the very densest regions, nuclear fusion starts, they heat up to tens of millions of degrees, and stars form. And these little white dots that you may be able to see flying out from some of the star-forming regions, those are newly formed stars. And this ran over hundreds of thousands of years. Next slide, please. So when you're collapsing due to gravity pulling you towards the densest region, go ahead. What stops the collapse? Well, everything was in motion. And so as you start trying to collapse towards something, you end up going into orbit around it. Next. And so you form a disk around the region of collapse, next, that is where gravity is trying to pull you in, and the centrifugal force from the orbit, the same force you feel if you take a ball on a string and whirl it around your head, that force pulling the ball out and allowing it to go into an orbit is the same force that keeps the disk up as well as planets. Go ahead. Anything that can collapse to the center, though, starts to form a sphere under the force of gravity. Go ahead. Gravity pushing inwards, pulling inwards, and thermal pressure pushing outwards. That makes a round thing, like a star or a planet. And planets, rather than thermal pressure, they're held up by material strength, but gravity still pulls them into a ball once they get big enough for gravity to be dominant. Next. So here is a gallery of, go ahead, all the disks in that previous simulation as they appear, and all the stars in that previous simulation. You can see that there's a wide variety of disks. Some of them you see as lines because we're looking at them edge on. Some of them you see as ovals because we're looking at them tilted on. And some of them you see as circles because we're looking at them face on. And this shows the variety of different ways that planetary systems can form. And that's something that we have learned over as we observe exoplanetary systems, is that every planetary system looks different. Next. If we look at the formation, go ahead, of one of these planetary systems, this is a set of simulations by my former student, Colin McNally, and by Tomoaki Matsumoto. We see a single disk forming with the gas swirling down to collapse onto that disk. And as we look inside and as the gas gets driven away by the newly formed star, we'll see the thin disk of dust and gas in which planets are forming. And here we can actually see the planets because they're driving spiral waves through the gas. So here we see multiple planets forming in a thin disk. And this is why all the planets that we see today are in a plane, because they all formed from the same dust in this disk. And so you could think of this as Mercury, Venus, and Earth as they are forming. And this was drawn from the current planetarium show, which I hope people will be able to see one of these days, maybe next fall. Next. Okay, so those were computer models of disks. What do disks really look like? On the left, we see a variety of disks that were imaged by the Hubble Space Telescope. And again, these are seen at all angles, and the disks themselves are the little dark or bright things right in the center. There's a lot of structure around them from ionization by the stars. But for the most classical one might be the edge-on disk at the bottom, one from the left, where you see an edge-on disk with the star shining out through it. On the right, the Atacama Large Millimeter Array directly images radio emission from the dust, and that shows us a almost edge-on disk, where the dusty disk in the center is obscuring the star, but then the star is lighting up the atmosphere. And this disk is bigger than our entire solar system. You can see the orbit of Neptune to the right there, and the disk is almost twice as large. Next. Here's if you will, a rogues gallery of different disks. These were all observed with the Atacama Large Millimeter Array. They weren't lined up in the sky like this. These are just postage stamps lined up to show us all these different disks. But you can see the planet formation, again, provides a wide variety of different shapes and structures. And each one is associated with planets in different places, of different sizes, and of different properties. But they all form from the dust that came in with the gas in these disks. Next. Now, what's going on inside one of these disks? Okay, so now we're going to have to think a little. On the left, I'm showing a model of a small portion of the disk. And go ahead and run the video. We're actually looking at material. The portion is rotating with the disk. So material is coming one way and the other compared to the average motion of rotation. So we're seeing the shear in the disk. The inside goes faster than the outside. And what we're looking at is how many boulders, sort of people-sized boulders, there are in this disk, where red is more and blue is less and black is none at all. On the top, we're looking face down. On the bottom, we're looking side on. What we're seeing is that the boulders tend to concentrate due to something called the streaming instability, which is kind of like bicyclists riding behind each other in a bike race. The ones in front push the gas away and allow the ones behind to come in. That brings so many boulders together that gravity can draw them together, and you start to form a larger object. And that gravity, as it brings all the boulders in, they clump up into bigger and bigger objects until you get what we call planetesimals. Very small building blocks of planets. Well, not that small, but maybe New York City-sized building blocks of planets. In the far outer reaches of our solar system, these planetesimals never formed planets, and so we have been able to visit them. This one in the center, called Arrokoth, was visited by the New Horizons probe after it flew by Pluto. This object is basically the size of the New York metro area, and this is the farthest out object ever visited by a spacecraft. So we're now in the far outer reaches of the solar system in what we call the Kuiper belt, beyond the orbit of Neptune, beyond the orbit of Pluto, where Eris and Sedna live, the two other dwarf planets. This object's very strange shape is characteristic, it turns out, for the collapse of bunches of planetesimals, because you get bigger and bigger chunks, and then finally they fall together. Another example of such an object is Comet Churyumov-Gerasimenko on the right. This was visited by the European Space Agency's Rosetta mission, which actually got a lander onto the comet that ended up bouncing around the comet because the gravity was so low, but was able to sample the comet. And again, we see this characteristic double-lobed shape from the gravitational collapse of boulders. These objects start themselves to collide and grow And eventually you get a few larger objects whose gravity is strong enough to start attracting all the other planetesimals in their orbits, where you get a period that is called oligarchic growth. The biggest ones get bigger and bigger. Any economic analogies are perfectly welcome. If you go to the next one, we see the final stages of that growth when major planets are still within reach of each other, go ahead, and will start to collide. So this is the very young Earth as it was about to be hit by another planet about a sixth of its size, so more or less the size of Mars in our current solar system. And oh my goodness, that happened, as far as we can tell, in the early solar system, and the result was the formation first of a disk of boulders and then of the moon. So the moon formed from these boulders, or from all the rock that got bashed off our planet by this final major collision. And there's clear evidence of other planets having undergone major collisions as well. This appears to be the final stage of solar system formation. Over a period of about a month, the moon coalesced from these objects. At the time, it was in much closer orbit with the Earth than it is now. So there's the young moon closely orbiting the young Earth. But over time, the moon has moved away from the Earth over billions of years and reached its current orbit. It moves away because it loses energy to dragging the oceans around the Earth. Next. So how long did this all take, the planet formation? Well, let's compare to a human lifetime. Say you have a teacher who's 46 years old, and it took them 9 months, 3/4 of a year, 0.75 years, to be born. Compare that to the sun and planets. They're 4.6 billion years old, which you could think of as 46 times 100 million years old. So instead of 1 year per year, get 100 million years per year. Their birth was about 5 million years. Disk collapse, formation, planet formation. That's only 0.05 of 100 million years. So that would be like being born in a few weeks for a person. So planets actually form a lot faster than people. Next. Okay, these processes are still going on in our solar system today. This was a comet, a very strange looking comet that was discovered in 1993. This comet was discovered by Carolyn and Eugene Shoemaker and David Levy, so it's called Comet Shoemaker-Levy, and it's the 9th one they discovered. And it was discovered in orbit around Jupiter. It turned out that this object had been torn apart by coming too close to Jupiter and was on course to hit Jupiter, to add to Jupiter's mass, just as happened in the early solar system. Next. So what happened when that comet hit Jupiter? Here are some models that I did back then. On the left, we have a model that's more or less the size of Manhattan. Go ahead and run it. I put a scale bar in there for comparison. And this is what happens to the comet when it enters the Jupiter atmosphere. It gets torn apart and spreads out. The gas inside that shock wave is heated up to 30,000 degrees. As a result, on the right, we see another model. This one is rather larger. It's kind of the distance, almost the distance from New York City to Chicago. And this is the result of a kilometer or so of 30,000 degree gas being inserted into the Jovian atmosphere. Go ahead. You get an explosion that covers the distance from New York to Chicago and blows completely out of the atmosphere before coming down and falling back down onto the top of the atmosphere. As a result, go ahead, of all those comets hitting Jupiter, this is what it looked like right after. All those smoke clouds that we see towards the bottom of the planet, the dark spots they aren't normally there. Those were clouds left after those explosions. So these are the results of the impacts on Jupiter. And this is the end, the final stages of planet formation. They're still going on today. Go ahead. And they're even still going on, go ahead, on our own planet. So here we are back at the planet Earth. And if we come down onto the planet, we will find evidence that planet building is still going on. The Earth is still growing. It's still accumulating mass, although obviously at a much, much slower pace than in the early days. And that's a good thing, because when it does accumulate mass, it can make a bit of a mess, as we shall see. So here we are in the American Southwest, and we're zooming in on a particular place. And whoops, let me stop and look at Google Maps to make sure I'm zooming in the right place. Here we are. And as we come in, we see Meteor Crater. So this is a crater left by an iron meteorite that came slamming into the Earth quite recently and added its mass to our home planet. Okay, so that was the story I wanted to tell. We're going to welcome questions, and if we go to the next slide, I will note that the introductory and final movies were things I made a couple days ago using OpenSpace. OpenSpace is a freely available program under development. It's in beta. It sometimes crashes, but it can do amazing things. It allows you to fly all the way from the surface of the Earth, as you saw. You can keep flying out into our galaxy and even beyond, into the realm of the galaxies and out to the cosmic microwave background. So the entire observable universe. This software is freely available. You'll need a reasonably powerful computer to run it, but I encourage anybody who's interested to go ahead and join the community and start trying it out. I am happy to take questions at this point. I'm afraid Eliza has a little bit of feedback. Oh well. Okay, well, I see that we have a first question. I work with NASA, so I did actually spend a couple of years as a postdoctoral fellow. Oh, the first question is, do I work with NASA or at NASA? And the answer is I work with NASA. I did spend a couple of years as a postdoctoral fellow working at NASA's Ames Research Center, but since then I work with them. I get grant funding from them to do research, and I use data from their telescopes, like the Hubble Space Telescope. Another question, how big is the sun? The sun is very big, very, very big. It is over, let's see, it is 1 million times the mass of the Earth. So if you think about how big it is across, it's about 1,000 Earths across. It's even big compared to Jupiter. It's 1,000 times Jupiter's mass, and Jupiter's pretty big.
Mordecai, I have a question for you that someone submitted named Rose. Have you ever seen an exploding star?
Yes, we have seen exploding stars. And in fact, we see them every week or two. So stars explode as supernovae if they're very massive, much more massive than the sun. What happens is they burn all their fuel. All the nuclear fusion in their center comes to an end, and so they start collapsing again. And if they're very massive, nothing can stop that collapse until a neutron star or black hole forms at its center. While it's forming, the surface bounces out, and you get a huge explosion, as bright as our entire galaxy for a couple of weeks. These are called supernovae, and if you look, one hasn't occurred in our galaxy in the past 400 years, but if you in a neighboring galaxy, the Large Magellanic Cloud, there was one back in the 1980s. And if you look out across the universe, which astronomers now do, We can find one in some distant galaxy pretty much every week or so.
Wow, that's pretty awesome. So Jane asks, are you able to predict when these masses are going to hit the Earth?
We are trying hard because mass hitting the Earth has been very dangerous to past ecosystems. For example, the dinosaurs almost certainly got wiped out when a 10-kilometer asteroid hit the Earth off the coast of Mexico and drove kilometer-high tidal waves across the oceans and blotted out the sun, first with a rain of fire and then with dust in the atmosphere. But there are actually efforts by NASA and other international space agencies to find all the large objects whose orbits cross the Earth, and we're well along the way there. At this point, I think we know everything above a kilometer that could possibly hit the Earth. I'm happy to report that none of them are on track to hit anytime soon at all.
Wonderful. That's reassuring news. Great. What's your favorite planet, Mordecai?
What's my favorite planet? Well, there are some wonderful planets out there, but I have to say my favorite planet is the one that's not too hot like Venus, not too cold like Mars, has enough liquid water on the surface to be able to go swimming, but not so much that you'll drown like Europa, which is covered in ice and then 100 miles of ocean. I like Earth.
Yeah, I agree. Earth is my favorite planet too. Okay, and then I think maybe last question for now is how did you get interested in planetary sciences?
Frankly, I probably read too much science fiction as a kid, and I also grew up during the beginning of the space age. I was 6 years old when the astronauts walked on the moon, and so I think that excited me as a kid. And now I continue to be interested because this is how we learn about our universe.
Wonderful. That's very cool. And you mentioned you're going to stay on and ask or answer other questions, correct?
Yes. So I will go ahead, and if people want to submit any other text questions in the Q&A box, I'm going to try to work through them and reply to them. So please go ahead and please keep paying attention to the Q&A box if you submit a question. I'll try to get to them.
Okay. Oh, and then there's one new question that came in that I think that since we have a little bit more time, we can have you address. But can you tell us the name of the biggest star that you've been able to identify?
I can certainly tell you the names of big stars. The problem is the name of the biggest star we know about is a designation rather than a real name. It's something like VV286. I'd have to look it up to be sure. Some big stars that have names are Betelgeuse, which is a red giant, and Rigel, which is a blue supergiant. And those are both bright stars that you can easily see naked eye. Betelgeuse, you can see in Orion's shoulder, even from New York City. And those are each, well, Betelgeuse, if I remember correctly, is bigger than the orbit of the Earth. So tens or even hundreds of times as big as the sun.
That means that Betelgeuse is the size of our our 365 day rotation around the sun.
Yes.
That is giant. I can't even fathom that. That's
it is
very
giant.
Cool.
And that's not the biggest star we know about. The very biggest stars are out to like Neptune.
Wow. But so how many light years would Betelgeuse be from planet Earth?
Betelgeuse is, I don't know the exact number, but it's probably several hundred light years.
Wow. And can you explain what a light year is?
A light year, the fastest thing that travels is light. Nothing can travel faster than it. How fast is it? It's so fast that from the Earth all the way to the moon takes about a second. From the Earth to the sun takes 8 minutes. From the Earth to the nearest star takes just over 4 years. So we measure distances that way by saying that that star is just over 4 light years away. The distance that light can travel in a year.
Okay, so that means that the light that we are seeing from the sun is actually from 8 minutes ago.
It was emitted 8 minutes ago and spent 8 minutes traveling to us.
Wow. So then if we are seeing a planet with a telescope that is 5 light years away, then that means we are seeing an image of what happened 5 years ago.
And this extends all the way out across the observable universe. We can still see light that was emitted at the beginning of the universe, right after the Big Bang. It's coming into us as what we call the cosmic microwave background. Those are that's light that's 13.6 billion years old.
Wow. So we don't even know if those planets exist anymore.
Well, anymore is a funny concept in a relativistic universe. You actually think of anything that's connected by light as being at the same time, simultaneous. So it's hard to say that's history when in fact it's connected to us as being simultaneous.
Okay.
Sorry, we're getting into some fairly deep concepts there.
No, it's good.
Mordecai, this is Pat again. I have a question. What's the process like for naming some of these stars? Like who decides Betelgeuse, for example? I love that name.
Right. So the historically visible stars were named over time by our forebears. Betelgeuse is a Arabic name. As it was actually, it's not actually pronounced that way, but it's an Arabic name whose pronunciation got butchered by European astronomers and then passed down to us. A lot of the stars got named that way. And then more modern times, the International Astronomical Union regulates how we designate stars, but they're much more likely to come up with catalog numbers now. You know, somebody goes out and maps a bunch of stars, and then we say, oh yeah, in that catalog, this number star. Usually the catalogs get named after the initials of the people who made them.
Great, thank you.
And one other question, even though we know that Earth is your favorite planet, Rocco asked if we would be able to live on Mars.
That is an interesting question. So Mars does have an atmosphere. It's mostly carbon dioxide, and it's only about 6% the pressure of Earth. So trying to breathe on it would be impossible. However, you don't need very much of a spacesuit to walk around on its surface. It would be like flying in a high altitude plane, like an SR-71 or something. And you would need a pressure suit, you would need an oxygen tank. The temperatures on Mars are uncomfortable but not unbearable. They're probably no worse than, say, the South Pole. Nighttime temperatures might be minus 100 or so Fahrenheit. Daytime temperatures can get all the way up to freezing in the nicest places. There is actually evidence of liquid water occasionally in little trickles on the surface of Mars. Could we live there? Well, yes, in principle, but in principle, we could also live in the bottom of the sea. And I don't see people flocking to live down in the Marianas Trench or something, which actually would probably be a less unfriendly environment because you don't have to worry about the radiation that bombards the surface of Mars. So yes, people could, but it would be like a more extreme version of living at the South Pole or under the sea. Probably not going to be very popular.
Yeah, I was about to say that doesn't sound very fun. We wouldn't have the beautiful ocean and all of our marine life and wonderful forests and tropical birds.
You'd have to bring your own.
Yeah, sounds kind of boring, actually. Maybe since this is an office of...
Beautiful. It'd be like living in a desert.
Yeah, which deserts are beautiful. But, you know, since this is the Office of Sustainability, we have to say, let's protect our Earth, right?
Absolutely.
All right. All right, Mordecai. Any last words? Anything you want to add to the students, your fellow students of the Department of Education, and maybe anything they can
say that I got a great education in the New York public schools, and I hope you will as well.
Awesome. Thanks so much for joining us. We really appreciate it.
And I'll go ahead and answer some of the written questions.
Awesome. Thank you.
Thanks.
You're welcome.
So we'll just take a few minutes to answer some of the written questions and then we'll move along. Does that sound all right, Lisa?
Actually, you can go ahead and move. I'm going
Right.
to be answering while the next speaker goes.
Beautiful, love it. Well, thanks again, Mordecai. It's always fascinating to zoom out. I think we can get kind of stuck in our day-to-day. So it's always great to get a new perspective and a widened out perspective. One thing I wanted to mention that I didn't mention in the beginning to everybody in the audience, if you're having any tech issues or if you weren't able to join us at the beginning, maybe you're hopping in a little later or you have coworkers who are, we will be recording this session and sending it out afterwards, so you can always watch it that way. I think another interesting aspect to these presentations is so many of them are tied up in history. We think of sustainability as science, but a lot of the time there's history involved as well. So that takes us to our next presentation. It's using geologic cores to tell the story of the past. Happy to have Dr. Lauren Neitzke Adamo with us. She's the co-director of the Rutgers University Geology Museum. And Lauren, I'm going to go ahead and turn things over to you.
Okay, great. Can you guys hear me? Yes.
Yep.
Okay, thumbs up. So make sure everything's working. So yes, hi, my name's Dr. Lauren Adamo, and I thank you, this Sustainability of New York City group. Sorry, I forget the full name of the, but thank you for having me so I can give you a little talk about something that I hold near and dear to my heart, which is geologic cores. So you can go to the next one. So just a little bit about me. As said, I am the co-director of the Rutgers Geology Museum. So we're just a little bit south of New York City. So when things return to normal and we can actually visit places like museums again, come visit us. We are a free geology museum open to the public. I'm a professor at Rutgers as well. I teach geology courses and a variety of topics, things like dinosaurs and planet Earth and all kinds of fun things. Just some fun facts about me. I do love dinosaurs as I teach the class and I work in a museum where we have dinosaurs, but my favorite dinosaur is the Triceratops. And for minerals, because I'm a geology nerd as well, which I love rocks and minerals, mica and garnet are my two favorite minerals. Okay, next slide. So what are cores? Okay, this is a term that is used a lot when you're learning or trying to research the past or think about how we try to unravel the geologic or climate history of the past. Cores are often used for this. So, definition according to Wikipedia is a core is a cylindrical section of a usually naturally occurring substance. Most cores are obtained by drilling with special drills, etc., and they can be things like sediment, rock, etc. So you can take core material of a lot of different things. I'm only going to talk about the cores today that relate to geology. In this picture, you can see that is actually me many years ago aboard a ship. And what I'm doing is I'm loading the multi-core. It's the thing in front of me. You can see there are long tubes there. And if you look right above my head, you can see all those weights on top of that metal frame. So that's actually looks like a pyramid, and it goes over the side of a ship, and those weights push it to the bottom of the ocean floor. And so those multi-cores are open, and they will catch sediment as one type of geologic core that we can use. But I'll talk a little bit about the different types of cores that I'm interested in. Okay, next one, please. So one type of core that you can use are tree rings. And if you've heard about tree rings, they're very useful to scientists because they give you a lot of information about the past. You've probably already heard that, for every year that a tree is alive, it adds one ring to its trunk. And so if you cut a tree and you look at the rings, you can count how old that tree was. But again, when we're doing this, we do not want to kill trees to study the past. So this is a method of coring into a tree where you basically just like drill with a tiny corkscrew into the tree, and then you pull out these long kind of pencil-shaped cores. And this is a way to core the trees without cutting them down, because we don't want to do that. So you can also take tree ring cores of ancient trees, things that have died in the past. So trees are one type of geologic core. Okay, next slide, please. So this is the type of core that I work with the most, which are either sediment or rock cores. And the one in the center, you can see it looks like just a gray mass, but what you're looking at, that's actually mud that was collected from the bottom of the ocean floor. So when it was collected, it was a full circle, and then when it was brought back to the lab, they're cut in half and opened up, and then you see there's those little holes in the core. Those are places where I took samples of them so that I could then analyze how the different properties in the cores changes over time. The tiny one that has some water on top of it, that's actually a tiny little core from the bottom of a water body. So you can have really long cores or you could have really short cores. And then on the other side, that's actually a core of like hard rock. So this is a type of thing that's harder to get into. You can't just push something into hard rock. You actually have to have a machine that will drill down into the rock to collect it. Okay, next slide, please. So another type of core that you may have heard of are ice cores. And so ice cores are collected in places where there's large accumulations of ice. So these would be in places where there are glaciers. So these are collected in places where there's continental glaciers, where the ice covers the entire continent, places like Antarctica or Greenland. But it can also be collected in mountains where there might be a smaller glacier in a mountain like the Andes Mountains or the Alps or things like that. These are especially hard to work with and especially expensive to collect. If you look in the picture, you can see those people are very bundled up because clearly when there's ice, it has to be collected in some place where it is very cold to keep keep it frozen. And the one that you can see, the shelves, that's actually a freezer that has the ice cores stored in them so that they stay cold, okay? Because if you increase the temperature even by a small amount, you no longer have an ice core, you have a puddle of water. So it's really cool because it can tell you a lot of really cool stuff about the past climate history of places. We have climate history records from Greenland and Antarctica that go back almost 1 million years from cores just like this. Okay, you can go to the next slide. So this is a picture of me actually in an ice core facility that you can see I'm all bundled up. And then if you look behind me, you can see the people behind me are even more bundled up. So to work with these ice cores and something like this, you have to work in basically a large freezer. So if you've ever been to like a kitchen of a restaurant where they have like really big walk-in freezers, that's pretty much where you're doing your science in one of those large freezers. And it can be, negative 20 degrees in these places. So you have to bundle up and wear lots of equipment when you're working with these cores. And then the other picture, can you go to the next slide? I think yeah, so that is a close-up picture of some of the ice from the core. And you see those little like round things? That is actually real air that is trapped in the ice. So ice cores are really cool because it actually traps with these little bubbles in the ice, little samples of the atmosphere from the past. So scientists will take these cores and they will melt this ice and release the gas and analyze the gas, and that can tell us about what the atmosphere was like during the past. So they can tell, you know, what was the carbon dioxide concentrations in the past. They can tell things about, you know, were there eruptions in the past, etc. There's a lot that can be told from analyzing the different properties in this ice. Okay, you can go to the next one. And you can even have cores from the moon. Okay, so these images are from NASA. This is not work I do, but if you look at the picture of those 3 women, the one on the right, that is one of my good friends, Dr. Yuli Gross. She's a professor here at Rutgers. But right now she is working for NASA in Houston, and she's the deputy director of the Apollo samples. And her and those 2 other women you see in the picture were responsible for opening cores that were collected from the Apollo mission 50 years ago. And these samples have been in a lock and in vacuum so that they don't get exposed to the air of Earth. And they kept them locked up for the last 50 years because they knew that if they analyzed them in the future, the technology would be way better and they would get a lot more information out of them. And so that's why they you know, I think it was last November is when they took this picture, when they first took these samples out. And that picture you can see, those are X-rays of the cores from the moon, and the one on the it's the same core in both pictures, but the bottom one was the X-ray taken in the 1970s, okay, and the one on top was the one that was taken last year. So you can see just how the X-ray, just alone with that one technology, has improved drastically over the last 50 years. Okay, go ahead, next slide. So I'm not going to spend too much going into some of the exact results of what we found with cores, but a lot of times when you're looking at cores, and I think you'll see slides like this in the next talk, because she's probably going to be talking about samples of corals from the Caribbean that will show this, but this is just one example of like what type of data you would get from one of these cores. So this record is actually from not just one, but it's from many, many cores all over the world that have been averaged together. And you can see that this is oxygen isotopes, and oxygen isotopes are used to indicate how the temperature changed in the past, and also how much ice there was on the Earth. So are we in an ice age, or are we in a warm period? And you can see that it goes up and down. So there's been changes through time. So if you look at where it says 1, okay, that's the stage we're in now, okay? And we know, if you think, it's warmer than it was. And if you go down to 2, that is the last glacial maximum. That's when we had the last ice age, about 20,000 years ago. So I drew arrows on the side that when we see the results that have up on this part of the scale, that indicates those were times in the past where it was warmer, sort of like we are today. And if it's on the other side of the scale, those are times when it's colder, like the last ice age. So if you've seen the movie Ice Age, think that type of environment. Okay, all right, next slide, please. Okay, so this is an activity that teachers, you can do. This is a little link here, but if you search Life Core activity, this activity will come up. And I actually have one to show you. So this was an activity that I was given to do in a professional development that I did a couple years ago. We were given these tubes and we were told to fill them with stuff to represent what had happened in our life over time to get to that workshop we were going to. So I made this thing. I know it's going to be hard to see, but I can share a picture later, which has all different stuff in it. Okay, so here's the bottom of the core. So at the bottom of the core, I put pictures of me and my family as kids, me as a kid, my parents as much younger, going to geology places and looking at rocks and stuff. That's how I first got interested in geology. And then I have a picture of Rutgers because that's where I did my school. Then I have some pictures of some actual rocks and fossils to indicate the time that I spent at school studying to become a geologist. Then here, this is actually a little bottle that has a little thing of mud from the ocean floor from when I went to sea. And then there's some dinosaur figures at the top that represents when I got my job at the Rutgers Geology Museum. So why do I show you this? Why is this important? Well, I have made kind of a fake core for you, okay? So these objects in here are not the actual events in my life, but they're an approximation. They're something that represents an event in the past. So you might have heard the term proxy. Okay, so proxy, this is what scientists use. They're a measurement. So this can be a measurement of the chemistry. It could be something physical like the color or the density or things like that. It's a measure of something that can tell us something about the past. So like this picture of Rutgers isn't actually Rutgers. It's a picture representing when I went to school at Rutgers in the past. Okay, you can go to the next slide. So this is just another example of this, all right? So in the center we have our core, okay? And I'm gonna kind of walk through some principles of how we understand cores, okay? So go ahead, next slide. So if I gave you these emojis and I told you to put things in order of how your day went using these emojis. So again, these emojis are the proxies. They're not the actual things you did, but they represent what you did in the day. So this is what your day might look like, okay, where you ate breakfast, etc., went to school, played video games, so on and so forth. Okay, so go ahead to the next slide. So what this is showing, can you go to the next slide too? Sorry, I was going to give you the definition. So this is illustrating the principle of stratigraphy, and this is some of the things that we use to understand geologic time. So the first thing is the principle of superposition, and this states that when you look at cores, the oldest layer is on the bottom and the youngest layer is on top. So yes, thank you. So when you look at this, you have the sand being deposited first. That's the oldest layer, and then the one that's deposited last is going to be the youngest layer. And the same thing with this core I showed you here, and the same thing with those emoji cores that I showed you too. So you can advance 2 slides, I think. Yeah, so if we go back to our core again, here was that one day that we represented. So let's see what happens when we add another day. So go ahead and add another day. So here is your day 1 and your day 2. Okay, so there are some things we can see. The oldest event in this case would be the coffee cup all the way over on the right hand side, but if you tilted it up, it would be on the bottom, okay? And the youngest event would be at the top or all the way to the left, okay? So go ahead, let's see what happens if we asked another person to make this core. What would their day look like? So go ahead and let's see if the emojis come up. So here we go. Here we have a core from one person and then a core from maybe one of your friends. So if you look at these together, we can both see that there's an oldest layer and a youngest layer in here. But if we start to compare the cores to each other, we start to see that things look similar. So go ahead, let's put some of these things up here. Keep going there and go ahead and one more. There we go. So what you can see here is I marked things that were the same. So these are events that happened at 2 different places, but they're the same event. So you might be at your one home and your friend's at their home, but you guys both woke up, okay? And that event is recorded in both cores, okay? And then you had your days, which you can see the donut, the school, the art thing, or the banana dog and the emoji face. You both had that day, but the days look a little different at each site. But then if you keep going up, you can see that the events are correlated. We can match the same events in those 2 different cores. The other thing that we can see is that we can see cycles, all right? So your one day, that is one cycle. It starts with a coffee cup, it ends with a sleepy emoji. And then if you go to the next day, you can see that same thing happens again. And this might seem silly and not, it might not be like, well, of course this makes sense with emoji, but these are things that geologists look for in cores. They look for events that occur in many different cores. They look for cycles to see how things repeat over time so that they can start to make sense of what happened in the past. Okay, you can go to the next slide. So I'm not going to go through all the details here, but this is a much more complicated version of what we just did with emojis. So here, this person is showing 4 different cores, and instead of fun smiley faces, they have labeled different geologic layers like Q3A, etc. And you see those red lines that go across? That is them correlating when different events happened in the past, okay? And that they have noticed those are the same events throughout each of these cores. So if you look at each core individually, they all look a little different because what happened at each location is going to be different. Your day at one place and someone's day in California are going to look very, very different, but you still have the same cycles where you woke up, you went to bed, and you might have events that affect you across the whole world. Okay, so go to the next slide. So another thing that this is doing, it's helping us to put some age context into geologic layers. So a question I get asked a lot when for geology is, how old is this? Okay, well, here's this rock. Can you tell me the age of this rock? Well, no, I can't tell you the age of the rock specifically, but I can, if I know where the rock came from, or if I know where other layers are in relation to it, I can tell you something called relative age, okay? So relative age is something that we do, and actually I did here with my core. I told you that this part of the core is older than this part of the core, okay? And so relative age, can you just go to the next slide? So relative dating is when you say something is older or younger, but you don't give an exact age. And these are things that are done through, like the rule of superposition and other principles of stratigraphy, where we compare rock layers. Go to the next slide. Versus something like absolute dating. This is when we use actual numbers. So a lot of times people want me to tell them a rock is, oh, this rock is 65 million years old, or this rock is 10,000 years old. I can't actually tell that by looking at rocks. I can only usually give you a relative age, whether it's older or younger, of a rock or a fossil, you know, unless I have some other information. So go ahead and click the next slide. So absolute dating, this is when you assign a numerical age to something. You've probably heard of this before. If you've ever heard about carbon-14 dating, that's when scientists will take a little part of that material and they'll analyze it in a fancy machine called a mass spectrometer. And then they actually have a way of calculating, not exactly, but they get an idea of this thing could be about 20,000 years old, plus or minus maybe 500 years. For things that are older, they have to use other methods, other isotopes like uranium or lead or potassium to date it. Carbon-14 dating actually only works if the thing they're trying to date is about 50,000 years or younger. Anything that's older than that, you have to use some other type of dating technique. So anytime you see any numeric number on something in geology, they've done it through absolute dating. Okay. All right, go to the next slide. So why does it matter? Why do we care about cores? Why do we think about absolute dating or relative dating? Well, that's because we use all of these things to put together what is called the geologic timescale. If you've heard something like this rock is from the Mesozoic or from the Cretaceous or the Permian or the Ordovician or the Cambrian, all of those have a time context, and they weren't just made up. They were assigned ages and names based on geologists studying cores and fossils and rock outcrops all over the world in order to put them into a series of events. So they're using the techniques like I showed you with the emoji cores to look at the layers on the bottom, layers at the top, and they're analyzing them, and then they're comparing them to other things across the world to come up with this. This is a very complicated time scale, but you probably recognize some of the words that are on here. Most people have heard of like the Mesozoic or Jurassic. We all, because of Jurassic Park, most people know that word. Okay, go ahead, go to the next one. And yes, that is it. So I think I blew through that, so we have time for questions.
Awesome. Thank you so much, Lauren. That was awesome. We got a lot of really cool questions coming in.
Oh, great.
I think just starting off, you mentioned you showed your life core, you showed that a little bit. Can you talk a little bit more specifically about your path, how you got into geology, and then specifically why ice cores are so interesting to you, or why cores are so interesting?
So yeah, I grew up in New Jersey, so not too far from you. I grew up outside of Philadelphia. But when I was little, my parents used to save up to go on family vacations in the summer, and we used to go to places out west to like the national parks. We'd go to like the Grand Canyon or Mount St. Helens, or Bryce Canyon, or Yosemite or Yellowstone. Been to a lot of excuse me, a lot of those places, and I was blown away by the beauty and the things I'm looking at these out out in nature. And I always wanted to understand how those things were formed. How do we have the Grand Canyon? How can we have this giant hole? And I wanted to know more about that. So, and I always loved earth science in class. I remember very clearly in 4th grade learning about the theory of plate tectonics and learning how it caused earthquakes and volcanoes to form. And I just remember this like big light bulb going off in my head and being like, that makes so much sense. So between those travels, and I was also always the person that had my nose on the ground and up to any rock. I would put my face right up against the sandstone to and look at all the little details, and I just wanted to understand that more. So when I was looking at colleges, I decided to go to Rutgers to study geology, and I was very lucky that I was I was able to get involved in some research projects with professors there, and there's a lot of work on cores that's done at Rutgers. And I just found it fascinating because it's like a snapshot of what's beneath your feet. You can only look what's beneath you, but then you can use the through the use of science and engineering together to get this like really cool section that's miles beneath your feet. And so I got exposed to looking at cores and unraveling cores, and I just found it really fascinating. So I don't work with ice cores. I help teach a workshop on ice cores, but I love ice cores. My dream is to go to like Greenland or Antarctica and help them with like recovering ice cores. That's like my ultimate professional goal. But I do a lot with sediment cores, and mostly deep sea cores that are taken from the ocean. But I have helped with recovering cores that are from on land, where you're just drilling on land.
Very cool. Thank you. That's super interesting. There's also been a lot of questions coming in about what's the most interesting core you've ever seen. Like, is there an event in a core that you've seen that has really come across as interesting to you?
Yeah, so the cores that I've worked on the most, so for my research and my PhD, they represent relatively young geologic units. So when I say young, like I'm studying like the last 20,000 to 100,000 years, and to us that seems like a really long amount of time, but it's really not that much in terms of the age of the Earth. So my cores that I've worked at aren't super interesting to look at first because it's just a lot of gray mud. I showed you the picture of it on the slide. But this one time when we were opening the cores, so they were collected on a ship and then they were brought back to New Jersey, and we had to use these, we actually used power tools to like cut them open, and we had this one core that we just kept it kept breaking all the tools that we were using to try to open it. And we were like, what is going on with this core? And then we finally got it open and we split it in half. And there's all this mud, and smack dab in the middle of the core, there was this giant rock that was like fist size, just sitting there. It's this giant black rock that's like miles and miles and miles away from any type of land. And it's like you have all this really, really fine mud. It's like the mud that you would put on your face, like that kind of mud, or you would make like clay out of. And it's like, how do you get this big black rock in the middle of it? And the way that it got there is actually from icebergs. So my sites are in the North Atlantic Ocean. They're close to Greenland and Iceland, but still really far away. So to understand how it got there, basically you have a glacier that's coming to the edge of a continent, and then it breaks off as icebergs and it floats away from the continent. And as it melts, it drops all the sediment and rock that's suspended in the ice. And so basically that's how it got there. It broke off as an iceberg and it floated along, and then it melted and dropped this giant rock right at the point where we stuck the core into it. And I kind of thought that was like, so like, what were the chances of us picking that one rock up in this core that's maybe like this big? And I'm not kidding you, it was the size of my fist, this rock. So that was a really cool thing.
That's so cool. Speaking of finding things inside of the core, there's a lot of questions coming in from Mateo and Jay and Marissa about, have you ever found like fossils inside of cores? And B, have you ever found like living organisms or viruses or anything like that inside of cores?
Yeah, so great question. Fossils, yes, 100%. So I didn't show a picture of it, but I study the fossils in deep sea ocean cores. That's what I look at. And these fossils are not like dinosaur fossils or things that you would normally think of. They're actually microfossils. So these fossils are the size of a grain of sand. So when you see them, they look just like sand particles, but when you pull them up onto underneath a microscope, you realize they're very diverse. They're called planktonic foraminifera or foraminifera. There's planktonic ones, which means they live up at the water column, and there's benthic, which means they live on the ocean floor. So yes, I do a lot with the fossils, but you can find bigger fossils in these cores. If you're coring through rocks, you can definitely core through sediments that have fossils buried in them. Excuse me, I have the hiccups. As far as life, so we have pulled up life from the ocean floor. So I have gone on a ship on a cruise to collect these cores in the middle of the ocean. And I remember a couple times that picture in the beginning I showed you where I was like loading that pyramid shaped thing. So those just collect like the top 2 to 3 feet of the sediment. And so right at the layer at the top where the sediment is with the ocean, there are often things living there. And so a lot of times when we would bring those up there, we would capture something in the core. I remember we brought up a starfish once. We brought up some fish by accident. We brought up some like mollusks and things like that. But the farther down you go, the less likely there is going to be life. So animals do burrow into the sediment, so you will get like worms and things closer to the top. But the farther you go down, you would not have life in them. And again, I don't look at the bacteria, but I don't know how far down the bacteria would be. But with a lot of these geologic cores, we're talking about things that are millions, even billions years old. So you wouldn't have living bacteria, but you might have fossilized bacteria in those.
That's really cool. I would not think of fossilized bacteria. Going back to the beginning of your presentation, a lot of students were asking about the tree ring cores. Abby and Veronica were asking, can you like go into a little bit more detail about how that's done? There was a lot of questions about, does it hurt the tree? Can the tree heal from it? Kind of how does it work? Like getting the tree ring cores, things like that. So
again, that's not a process that I've done, but they're basically taking out a piece that's like the size of a pencil, and they kind of like, it's almost like a corkscrew where they screw into it, and they're taking just a little. It's small, not even as round as your pinky. So yes, the trees can recover. They do that specifically so that they won't die. They don't want to have to chop the tree down to get those. But yeah, I mean, if you've seen, trees are pretty resilient. They've grown around other trees or around metal, and trees are pretty resilient. So that little bit is not going to hurt them.
Cool. That's good to know. We don't want to be hurting trees in this.
No. I mean, if it's already dead, then yes, you can take the full, but you don't want to cut it down for this. Yeah,
makes sense. We have a little question about the symbol on your last slide. Charlie from Brooklyn was asking, what is that symbol? What was that a picture of?
Gotta have to go back to the last slide. I'm not sure.
On this one, the under question time.
Oh, sorry. I was thinking scientific symbol. So yes, that is a mastodon head. So our museum, our kind of icon of the museum is a full-size male mastodon skeleton. So his name is Manny the mastodon, not after Manny from Ice Age, but because he was found in Mannington, New Jersey. So he is on display at the museum. So that's kind of like our favorite thing. We show these pictures of him. So yes, when things return to normal, come visit Manny at the Rutgers Geology Museum. You can see pictures of him on our Facebook page and our Instagram. There's lots of pictures of Manny there.
Nice. Okay, I have one more question about other types of cores. So kind of two-part question. One, the moon cores that you showed a picture of, how did they get those cores? And then second part, are there other kinds of like crazy types of core samples that you've seen out there?
I mean, you can take core samples of anything really you can drill into. When I was putting this together, I saw that like sometimes they'll take cores of like living bone tissue if they want to like biopsy it. But yeah, there are no Mars cores. I know that. Someone asked me that last time I gave this talk. But the moon cores were taken from the astronauts. So the astronauts had equipment when they were there. They were actually trained when they were on the moon. Before they went there, they were trained by geologists on how to recover and to pick up to figure out which type of rocks to bring back. I don't know what apparatus they use, but because it is so short and because they wouldn't have been able to bring like a big drill rig, they probably had something that they either pushed manually or maybe they could turn it like a screw to collect just that top layer. So they're only maybe a couple feet long. They're not super long because the astronauts would not have had a way to get that equipment to the moon, set it up, and then bring the things back. They are trying to possibly recover cores from Mars eventually, like through the rovers and things, but that won't happen until there's something that can either send it back or where they physically go to Mars again and retrieve those samples from the rover. So that's still a far ways out, but that is something that NASA is currently trying to figure out, according to my friend who's there. I have no knowledge besides what she tells me.
So cool. I can't wait to see cores from Mars. That would be sweet.
Yeah.
All right. So I guess just to round it out, do you have like one big takeaway that students should be remembering about cores? One thing to remember for them?
I don't know. To me, if you look at one and you don't know what it is, it could seem rather boring, but it really is like, it's like a book. And if you know how to read it, if you know what to look for, it really tells an amazing story. So, if you get the chance, again, when the museums are back open, there's a wonderful exhibit on ice cores at the American Museum of Natural History explaining like how things can be analyzed through that. I highly suggest that you go see that. But yeah, it's not just rock. It's not just mud. There's a lot more to it.
Cool. Awesome. Well, thank you so much, Lauren. That was very, very interesting. It was very cool to get it.
And try to answer the questions as
Yeah.
well.
Yeah. If you could stay on, would be great.
I actually have a quick question for you, Lauren. So you were just talking about ice cores, and since so many of us have not seen ice cores before, I'm really curious. Like you showed that there are little air bubbles in the ice cores. So when scientists pull up those ice cores and analyze the air bubbles, are those air bubbles from present time, or is that?
No, it's from the past. So it's actual air from 800,000 years ago, however old it is. So I didn't show it because that's a whole nother talk about ice cores. But basically the way ice and glaciers forms is it over time will kind of form a little hole and trap a little sample of atmosphere. So that's really interesting because the bubbles are actually not a proxy. It's an actual measurement of the atmosphere. So all the other things like using the chemistry and things to try to figure out like an approximation of things in the past, those are proxies, but the air bubbles are actual recording of the actual atmosphere, which is neat.
So that's one of the reasons why we're able to look so far in Earth's climate and get like a pretty approximate sample of what
the atmosphere was doing in those the places they were doing.
Very cool. And what is what type of core goes back furthest in Earth's history?
Most likely rock cores would be the farthest. So ice. A continuous record only gets back in Antarctica about 800,000 years ago. It's a little less in Greenland. I can't remember off the top of my head. And then the ocean cores, because there is plate tectonics, it's being recycled, so it doesn't last as long. So the oldest cores would be like rock cores from land, where you would get, if you drill into like some of the oldest parts of the continents, which are called cratons, like usually the middle of continents, you can get pretty old rocks there. So billions of years.
Very cool. Thanks so much, Lauren. I really appreciate it.
Thanks for having me. I will answer questions now. Thank you, everyone.
Yeah, thank you, Lauren. I'm sending you a giant thumbs up emoji after that presentation. And I'm definitely going to have to make a life core after this. I'm a visual learner, so I appreciate the visual tools. And I think that's a great activity that students could do at home. You also made me think back from my childhood. I used to collect rocks and organize them in these boxes neatly labeled. My parents have been like, get these rocks out of here for probably like 20 years now. So.
Yes, my parents too. They were not happy. But now my 4-year-old has his own collection, so that makes me happy.
Okay, good. Pass it along. So it's getting warmer outside, and similarly, our next presentation, we're heading somewhere a little warmer. We're going to head to the Bahamas, which I'm sure is somewhere that we'd all love to be right now. Next presentation is Tropical Tales of Polar Ice, how studying rocks on the Bahamas can tell us about ice sheets. And we're joined by Dr. Jacqueline Osterman. Jackie is an assistant professor at the Lamont Doherty Earth Observatory at Columbia University. So Jackie, I'm going to turn things over to you. Thanks so much for being here.
Awesome. Thank you so much. Can you hear me? Is that working well? Okay, perfect.
Yep, I can hear you.
Thanks so much for having me. I'm really excited to talk to all of you today about some of the things that I work on and think about, and just kind of share a little bit about my kind of career path and my work with you. And yes, I will be taking you all to the Bahamas, which is where we were supposed to be about now if it wasn't for the pandemic. So we're a little bit sad about that, but we're hoping to return for more field seasons in the near future. So I thought I'm going to start with telling you a little bit more about me first. I'm going to go to the next slide. Yep. So as you might have already picked up on my accent, I'm not from the United States. So I'm showing you a world map here and New York City, where all of us are at the moment. And I'm actually from Germany, so all the way over in Europe, just shown by this red arrow. And in particular, I'm from a town called Munich, which you might have heard about from Oktoberfest or related activities. And that's where I was born and I grew up, and I went to school in southern Germany, and I did my undergrad and my graduate degree or my master's degree in Germany. And actually threw in a picture of the town where I grew up, which you see on the bottom right here, which kind of looks like a very old postcard. It's even kind of grainy. But this is where I grew up. It's a small town of 4,000 people, which is probably maybe a Manhattan city blocks worth of people. And it's close to the Alps, which definitely influenced my love for the earth and for nature and for being outside. But yeah, I was in Germany for my undergraduate and master's degree, and then I came to the US to do my PhD, and I went to Harvard for a degree in Earth and Planetary Sciences. I went back to Europe after that. I did a short postdoc or research position in Cambridge in the UK, and then I've been now at Columbia for the last 2.5 years, and I've really enjoyed it a lot. Next slide, please. So when I was a student, when I was in middle school and I was in high school and I was trying to figure out what I wanted to do with my life, I reflected on the things that I loved most doing, because that, you know, it helps when you like your job. And one of the things that I love doing is being outside. And I've always had a fascination with nature and with traveling. So all of these places, the top shows is in Patagonia, so in Chile. The bottom is Ireland, Barbados, Himalayas, Nepal, and the Dolomites. Those are all places that I've gone to, some of them for my job now, which is great, and some of them just because I like being outside. And I'm really fascinated by understanding how mountains form, how sea level changes, how the atmosphere convects, and all of these questions. So that's always been really fascinating to me. And then the other thing I liked as a student was math. So I really liked equations. I don't know how many of you can relate to that, but I really enjoyed doing maths. And so when I was in high school, I tried to figure out what can I do that allows me to do both of these things. And I thought a lot about a lot of different options, and it wasn't an easy decision. I wasn't like, I know exactly what I wanted to do. But I wanted to do something that has to do with both of these things. And so that led me to start with a degree in physics, where I could kind of explore my love of math and equations. And then I turned more and more to earth sciences. And that's mostly what I do now. So I do geophysics, which means the physics of the earth. And most of the questions that I work on today and during my PhD are related to understanding sea level change. Next slide, please. And it's a question that is very relevant today, which is how much will sea level rise in the future? How much is sea level rising today? And it might seem like when I tell people that I study sea level, it might seem like one very small and specific thing, but it actually is such a big Earth system question, because sea level, if you want to understand sea level change, you need to understand how ice sheets behave and how they melt. You need to understand how storms come through cities. A lot of you might remember Superstorm Sandy, the sea level change impact it had on the city. It also, sea level changes if a place like New York City is uplifting. So if the solid Earth is actually going up or is sinking into the mantle, which happens all over the place, all over the world, and we need to understand those processes. And sea level has changed a lot in Earth's history, from massive ice ages to very warm periods, and we want to understand all of that. So it's a very broad topic, and I'm interested in all of these different aspects that I just mentioned. But of course, it also has a very societally relevant side to it, and that's another part that I actually really like about my job, that it is both understanding something very fundamental and being just very curious about things and getting to travel a lot, but then hopefully also learning about something that's actually useful for people who live close to the shoreline. These are two pictures here from New York City, where flooding occurs quite frequently. If you go to the next slide, please, which is a map of New York City, and you can try to find where all of you are right now. So we have Manhattan, and we have the different boroughs in there. The dark blue is areas that are ocean. The light areas are land. And this shows you the current sort of shoreline with a tiny little bit of sea level rise. You see that number 1 in the bottom left, so sea level rise by 1 foot. And everything, all the land that's kind of shaded blue are areas that are kind of flooded if sea level rises a little bit. And all of these areas are areas that are actually flooded just if there's a very high tide, that are sort of marshland. Next slide, please. If we crank up that kind of sea level number to 3 feet, so this now, everything that's blue are areas that are flooded if sea level rises by 3 feet, which is a common projection for the end of the century. You see that more and more areas are kind of starting to be blue. You see that LaGuardia Airport is blue. You see areas, big areas in New Jersey are blue. You see that Jamaica Bay and the Rockaway areas are very blue. And all along Manhattan and Queens and Brooklyn, you start getting more and more blue colors, which means more and more areas will be flooded. Next slide, please. And this is the scenario, the sort of extreme scenario of 10 feet of sea level rise, where really large parts of New York City would be underwater. And so the question that my work's trying to answer is, how much will sea level rise and how fast? And that's what I'm going to talk about today. And the most significant, when we think about 10 feet of sea level rise, where does that actually come from? What is the biggest contributor to sea level rise? And if we go into the next slide, the biggest sea level, and play the video, please. The biggest contributor to sea level rise more and more, so already today, but more and more also in the future, is melting of polar ice sheets. So this is the Antarctic ice sheet on the right, and areas that are turning red are areas that are melting more and more today. And so we want to understand how fast and how much will these continue to melt into the future. And that's a very difficult question to ask. So there are lots of people who try to answer that question, and they run big computational models. They simulate the atmosphere. They go to the Antarctic ice sheet and study the ice and try to understand all of these processes. My approach is a little bit different. Next slide, please. So I want to try to answer the question, how high does sea level rise when the Earth warms? And when it warms by a few degrees or by a few degrees Fahrenheit. And the way that I approach this question is that I go back to times in the geologic history of the Earth. And it seems like you might have heard about some of those in the last talk. And I go to times that were warmer than today. And it turns out there were a lot of times in Earth's history where temperatures were actually warmer than today. And I tried to reconstruct how high sea level was then. So essentially, the Earth has done an experiment for us where it sort of cranked up the temperature, and we want to go back to those times, travel back in time, and try and extract and understand how high sea level was and how fast sea level rose and how high it rose. And the time period that I work on mostly, but also other time periods that I'm going to talk about today, is called the last interglacial. Next slide, please. So the last interglacial is a time period that is about 125,000 years ago. We are currently in a time period that's also called an interglacial, so in between glacials. In contrast to being in an ice age, if you think of the Ice Age movie where massive ice sheets cover the Earth, we are today in a period that's in between these glacials. And we want to go back to the last time Earth was in that configuration. Temperatures were a little bit warmer, 1 to 2 degrees Celsius, 2 to 4 degrees Fahrenheit. And the temperatures were warmer, which is an important point. There weren't people around that emitted a lot of CO2 and that caused climate change. They were actually warmer because of natural conditions where the Earth was positioned differently relative to the sun, where causing temperatures just to naturally be a little bit warmer than today. And we want to travel back to that time to understand how high sea level was then. Next slide, please. And I want to give you a little bit more context of, okay, 125,000 years ago, what does that mean? You guys all know how old you are. 225,000 years is a lot more than that. But actually, compared to how old the Earth is, it's not very old. So this is sort of a spiral of Earth's history where it starts 4.5 billion years ago, and we go through the first few billion years, not that much happens. 500 million years ago, the first forms of life sort of start in the oceans, and then they slowly creep on land, and then we have the dinosaurs, and then the Earth cools into the Ice Age, and then all the way at the end is when humans evolve. And the last interglacial is also pretty much all that way at the end, 125,000 years ago. So compared to most rocks that you will find when you walk around Central Park or most other places on Earth, the rocks that I'm going to be looking at, they're all very young. They're only 125,000 years ago. Okay, next slide, please. So the big question is, of course, okay, how do we do this? How do we travel back in time and understand how high sea level was? And so I'm going to walk you through how we do this. And I'm going to show you as an example how we do this in the Bahamas. Next slide, please. The Bahamas is an island chain that's between sort of Florida, it's shown here in purple, between Florida, Cuba, and Haiti. Next slide, please. I'm kind of zooming into this area now, where we keep Florida on the top and we have Cuba. And you see here the Bahamas. So what you will see is you again have these very dark colors, which are just the deeper ocean. And then you have the kind of, you have land, the green colors, and you see the different islands of the Bahamas. And then you also have this turquoise color, and that's very shallow water, so 10 meters, 20 meters. And so you only, if you dive down 20 meters, you hit sand essentially, and that turns this a little bit lighter than everything, than the dark ocean around it. And in the Bahamas, what we call this is, we call this our carbonate, which is the name of the material that forms these islands, our carbonate platform. So it's this platform, and parts of this platform stick out above sea level, and those form the different islands of the Bahamas. Next slide, please. And it's a truly magical place. If you ever get the chance, I can highly recommend it. This is just a photo from this, and you really nicely see this kind of sandy platform. So all of this turquoise is underwater, but very shallow water. And then you see sort of the islands kind of sticking out above sea level. And one thing that I didn't, so I went for the first time to the Bahamas last year. And one thing I didn't expect, I kind of had this image of, this is where all the resorts are and all the, you know, big hotel chains and a lot of tourism. And that's true, but only on a few islands. There are actually a ton of islands that are part of the Bahamas that are essentially uninhabited. I mean, few people live there, but no big towns. And you can walk for miles and miles and miles along beautiful beaches and don't see anyone, which is very nice. Next slide, please. So we're gonna try this. This is a video from last year, and we'll see if the file is very big, so it might be a little stop and go. So I'm just gonna talk you through it, and it might keep going or it might not keep going, but this already gives you a good idea. So the interior of the Bahamas are mostly vegetated, and it's almost sort of jungle-like. And we're looking at a coastline here. Some beaches are nice, sort of sandy beaches, but a lot of the beach is also very rocky. And you see this a little bit, you see this right at the front of this picture, but you also see it a little bit further in. It's not all just sand, it's also a lot of rock, right? And this rock is actually, the way this rock forms is by sand turning into rock. And this rock that you see here is actually 110,000 or 120,000 years old. I'm going to show you this a little better in the next slide. Can you go to the next picture? Thank you. So here now we're kind of zooming into one point along the coastline, and you see this concept of a beach turning into a rock kind of very nicely, I think, because you see these very flat kind of structures in the rock. And if you next time you go to the beach, have a look a little closer to the rocks and see what you find there. You might find these same kind of very linear features. And this is literally the beach, the sandy beach that turns into rock. And then you have a new layer of sand and it turns into rock, and a new layer of sand and it turns into rock. And you have this one after the other, and you form these really nice kind of layered sheets that you see here. Next slide, please. Sometimes these sheets aren't just flat, but you can also get these wavy structures that you see here. So these would be dunes. So if you think of a Long Island beach, maybe where you have some dunes and they migrate, so they move around, you know, over years of time scale. And you see these kind of waves in this structure here. And next slide, please. And now we're zooming in even further, and it's a little bit hard to see, but you see this kind of layering, and then there's some, materials transported off, and you have a new dune, and it layers on top, and it keeps layering and layering. And so this is how a lot of the this is essentially how all of the Bahamas are formed. And if you go along the beach, most of the rocks that you see that look like that are from the last interglacial. So we know there was a beach there 125,000 years ago. So that's already close, but we want to know sea level, right? We don't just want to know, okay, we were close to a beach somewhere maybe. We want to put our finger on this is where sea level was. So we need slightly better clues. Next page. Yes, so how do we do this? So next slide, please. So one way of doing this, and one of the best ways of doing this, is trying to look for corals. So if you've ever had the chance to, in the Caribbean or any other place in the kind of close to the equator where it's a lot warmer than here, and you go swimming offshore, you might find corals, and some of them are kind of soft and they kind of go with the water, and some of them are hard. And the hard ones, they actually, once they die, they don't disintegrate, they just stay there and they turn into rock. And specific types of corals, so if we find a coral today that has turned into rock, we know this coral was under sea level, right? Because they don't grow on land. And some species, we actually know that they really like to be very close to the sea surface because they need a lot of light, or they have other conditions where they just only grow when they're very close to the sea surface. And those are the types of clues that we try to find in the field. Next slide, please. And I'll show you some of these examples now. So on the right, you will always see kind of the modern coral if you go swimming today. And on the left, you'll see what we found in the Bahamas, which is the coral turned into rock, which makes it a fossil. So this is a coral called brain coral. And you can all guess why, because it looks like a brain. On the left, you still see this kind of brain structure, and you don't see it as clearly. There's actually sand that was deposited on top of it afterwards and turned into rock afterwards, but you still see very clearly this fossil coral. If we find this today, we can date it. We know it's from this time period that we're interested in. We know sea level was at least this high or higher, or a little higher at this location. Next slide. This is another type of coral. This is called an elkhorn coral because it looks kind of like the antlers of an elk. And on the left, you see the fossil, the dead version of it that is 120,000 years old. And you see essentially the little antlers, the smaller parts are broken off, and what remains is kind of the stem, the biggest part of it. Next slide, please. This is called a staghorn coral. Again, named because it looks like the antlers of a stag. And on the right is the living coral that you find when you go swimming today. On the left is the fossil version that you can find. This is actually not in the Bahamas. This is on Barbados, where you can find this broken up and jumbled up if you're ever anywhere in the Caribbean, I guess, but especially Barbados, you find fossil corals everywhere if you just look. Next slide, please. And this is the last coral I wanted to show you. So this is called a stony coral. Again, on the right, we have the living organism today. And on the left, that's already covered by stones and sand. But it's sort of peeking out on top of that, out of that sand, this like big feature of this big fossil stony coral. Next slide, please. There are a couple of other clues that aren't just corals that we can use, and I'll show you a couple of those. So, and you can just think, okay, if you go to the beach today, how do you know that's a beach, right? You know it's a beach because you're close to the water. Forget the water is gone. What else is there that in the absence of water could tell you that you're actually close to sea level? And this is an example here. If you go to a place that has a cliff, for example, the water and where the water surface is, it actually erodes into it eats away off the rock and it forms this notch, which you see on the right here. And if you go to any kind of cliff coastline today, there's a good chance that you see a small version of this or a big version of this today. And if we're lucky, we can find this dating to the last or from the last interglacial. So on the left here is from the Bahamas, where we ventured through the jungle to look for clues of sea level, and we found this huge erosional notch that formed when sea level was, and we can put our finger at exactly where sea level was, right? When sea level was at that kind of furthest part in of that erosional notch. Next slide, please. Another really good clue is kind of sandy ripples. Again, on the left, this is in the Bahamas, you have these kind of ripples that form along the beach, and on the right, sorry. And on the left, you see those ripples turn into stone. And so you see this on this sort of middle platform. I should have added an arrow here. On the middle platform, where you see a little bit of this wavy structure, you see there's some lighter colored modern sand sprinkled around it, but there's also rock that preserves that exact same sort of ripple structure. We know that only forms at sea level, so another clue for sea level. And the last one, next slide, please, that we can use are caves. So again, if you look at a rocky coastline today, a lot of caves. On the right is a modern cave that formed because the water erodes the rock. And on the left, you see these two. You see a cave that's just a little bit above sea level, and then you see some higher caves as well. And we can use those as well as indicators and deposits within, so stalactites and stalagmites, as indicators for for reconstructing sea level. Okay, next slide, please. So how do we know how high sea level was? Well, we can use these clues, fossil corals, notches, caves, to tell us that answer of where sea level was in the past. So I thought I'm going to walk you through what that actual work looks like. So conceptually, we have these corals and they tell us something about sea level, and so we can use them. But in practice, now we travel to the Bahamas, what actually happens? And I'm going to go through this step by step with you. Next slide, please. So the first step is to make a plan of where to look. So as telling you, most of these islands are actually not very much explored. There's no geologic map. We don't have a map that tells us, okay, here's a fossil coral. We don't actually know. We have a satellite picture. You can go to Google Earth and you get a satellite picture. Maybe sometimes we have a very good topographic map, so an elevation map of this island. But other than that, we don't by itself know where these clues are that we're looking for. So we have to think about, okay, is it likely that we have some corals, fossil corals here? How do we think they form? We go to a lot of places and don't find anything. And then we're like, okay, why didn't we find anything here? What can we learn from that? And we go back. So this is all from last year. And we had this giant map. And every evening we kind of thought about, okay, this is like a scavenger hunt. What did we learn today? Which clues did we find? And what does that tell us about where we should go and look tomorrow? So this is step one. Next slide, please. Morning comes and we take the car out, drive, we say, okay, today we're going to try this point, this spot along the coastline. And we drive out and then we just walk for most of the day. And you don't see us here, but we are in that picture. This is, again, a drone picture from a drone. And we just walk along the coastline and look for these clues. Again, it's kind of like a scavenger hunt. And we look at these rocks. Everywhere where we go, we have these rocks and we have these layers. And we try to understand, okay, is this a dune that formed on land? Is this a beach sediment that formed like right more or maybe below sea level? How thick are the units or how thin are the units? What is happening here what happened when these rocks formed? And we keep walking and we keep looking for fossil corals. Next slide, please. And then when we're lucky, we find these fossil corals. And literally, it's kind of like we're like looking for gold. It's like we're okay, maybe around the next corner, maybe around the next corner, and then we find them, we're like celebrate. So we find these clues. Once we've found this location, we kind of set up to do a very good survey of it. Next slide, please. And surveying means taking a lot of notes. So we all have our field books. We say, okay, what do we see? We describe what we see. Next slide, please. The next part is we take an actual sample. So on the left here is my grad student, Roger Creel, and he's hammering out a little piece of that coral. Also in the middle, you see small chunks of that coral taken out. And then on the right, you see at the end of the day, we have them all in the little bags to bring home. The reason that we take little pieces of coral is that we can actually date the coral. So we can find out at what time this coral was alive. So we want to only reconstruct, we want to here reconstruct sea level during this last interglacial period, 125,000 years. So we want to actually know, was this actually alive during that time period, and when towards the end or the beginning of that time frame. So to assign an age, we need to take a little piece home into the lab and do some analysis with it. Next slide, please. The next thing that we want to do is we want to reconstruct sea level, right? So we need to know exactly the elevation of where we are. So we take longitude and latitude, our coordinates, but we also measure elevation. And what you see here is essentially a fancy GPS. You see that little white thing on the top is the antenna. And it's sort of what the GPS in your car and your phone, it's just, it does a little better. So we take the exact elevation. Next slide, please. And then we take a ton of pictures and we actually fly a drone. So you see the drone in the left on kind of flying there in the air. We take tons and tons of pictures so that we can essentially take this outcrop and bring it into the lab and bring it home so that we can look at it later on. What you see on the right picture is this little white marker with the red cross. So what we do is we put all these little markers out when we fly the drone and when we take a bunch of pictures. And what this allows us to do is we put this all into a computer. We measure for each, where we have each of these markers, we measure the coordinates. And then the computer is smart enough with all of these pictures to construct a 3D image or model of our outcrop. Next slide, please. You see that here, let's see, this is a video. Let's see if this plays. Excellent. So this is the outcrop taken home. So this is all of these pictures stitched together. And now we have this in our computer and we can actually go in, go back. We use this for outreach a lot. We have an augmented reality headset where students can put on the headset and actually walk around the outcrop. And in parts, this is super high resolution. So we can actually, now that we're back home, zoom into and look at all of these features that we've analyzed and kind of go back and keep that memory of the outcrop. And we can remeasure elevations and reanalyze once we've gone back, come back from the trip. Next slide, please. And the last step is once we're back, we also do analyses on the samples that we take back, so the corals, and we do simulations. And on the right, you just see kind of the Earth motion within the Earth's interior. So I do a lot of simulations of how the Earth deforms, how much the Bahamas are uplifting or subsiding and changing sea level in those locations. So there's a lot of, once we have the data, actually understanding what they mean is a big part of this as well that I don't really go into here, but I just want to mention it. Next slide, please. So we've done this work and we've gone out last year and we're going to go out again to kind of continue this work in other parts of in other islands. What we found so far is that during the last interglacial, so when temperatures were 2 to 4 Fahrenheit warmer on average across the whole globe than today, that sea level was about 6 meters, so 15 to 20 feet higher than today. So small temperature change, a few degrees of Fahrenheit, actually caused quite a big sea level change. However, we don't know yet how fast that sea level rise occurred. And that also means it's important for us to know how fast that sea level rise will will occur into the future. What we learn from this is if we heat up the Earth by a few degrees Fahrenheit and wait 1,000 years, sea level will probably rise by 15 to 20 feet. But we don't know if this will happen over the next 300 years or the next 3,000 years. It's definitely not going to happen over the next 30 years. We know that, so that's good. And most of this ice is probably, most of the sea level rise will probably come from the major ice sheets, which are the Western Arctic ice sheet and the Greenland ice sheet. Okay, so I'm at the end of the time. I have used my whole allotment, but I have a couple of fun pictures I just wanted to show to finish off. Next slide, please. So along the way, of course, there are a lot of surprises that happened. We got caught in multiple rainstorms and thunder, which was a little scary because we were so close to the ocean. And this happened like from 1 minute to the next, and we just tried to wrap everything we had, like the antenna, in trash bags and get all of the samples. And actually the samples don't mind being wet, but the antenna does, and the drone does as well. We did lose a battery to water damage during this trip. So a lot of rainstorms. Next slide, please. A lot of mosquitoes. And they're actually getting ready there to try to make their way into the woodwork. And we had a machete and tried to kind of get through some of the wood just to go through the trees, just in the vegetation, just to find the outcrops that we needed to go to. Yeah, lots of mosquitoes. Next slide, please. We also encounter a lot of animals and people on the island. This was a dog that on one of the times when we just walked along the coastlines we encountered, and he followed us around for the rest of the day, and that was a very pleasant surprise, and we very much enjoyed that company. Next slide. We also saw some sharks, but this is kind of a mini shark. This is I think it's called a nursing shark or a reef shark. They don't really attack humans, but I didn't really want it to go that close, but Blake was brave enough to take a picture. Next slide, please. Traveling around these islands can be really fun because I was telling you that a lot of them actually don't have a lot of people living on them. So it's not trivial to go from one island to the next because not a lot of people do it. So for one of the trips, we chartered a little plane that you see here, which took just the 4 of us. And it was really fun. And the pilot, while he was flying, was texting. And we just thought it was hilarious. He was texting while flying. Next slide, please. And this is, I think, the last one. And this was also, I guess it's also an end one. Thumbs up. This was also a really fun day where we thought, okay, we really think this place has a lot of corals and has like a really good section of the last interglacial rocks and reefs. And so we really wanted to go there, but it was in someone's garden or backyard. And so everyone is out, most of the time people are very friendly. So we often just knock on people's door and we're like, oh, do you mind if we like just look on your beach for a moment? And they normally let us. And we did that a lot. And this was a beautiful spot. And I actually dreamt of this beach last week. And I wish I was there right now. And that's it. And I'm really excited to answer any questions that you might have about this fieldwork or my job or career path in general. And thanks so much for listening. I know it's Friday afternoon and the weather's getting nicer out. So thanks so much.
Awesome. Thank you so much for joining us. This was very, very cool. Very interesting to learn about. I never think of how the ice age and how sea level rise actually affects, the Bahamas.
Yeah.
In that way. It's so cool. So yeah, there's a lot of questions that came in about where you perform your field work. So you're doing this field work in the Bahamas. Can you explain I know you explained a little bit bigger why the Bahamas were important, but can you spell it out a little bit more about why this location?
Yeah. So I was telling you that one of the great clues are these fossil corals. So you want to go to a place that is warm enough that there was a reef in the past. So that sort of excludes a lot of coastline already. So we want to stay sort of in the tropics. And then this place actually has a lot of, I was telling you, okay, this is whole shoreline or this rocky coastline, and it all formed 100,000 years ago. The reason why so much rock formed there is because there's a lot of sediments, a lot of sand that's essentially like thrown on land and turned into rock. And that's very unique in the Bahamas. So other places in the Caribbean have corals as well, but there you actually have very fast accumulation, so a lot of sediment turning into rocks. And the more sediment turns into rocks, the more we have to work with and can see and analyze. And it's also because it's many little islands, we study the coastline, right? So if you have Cuba, which is a giant island, most of it is interior of the land. We want lots of little islands where there's lots and lots and lots of coastline that we can explore. So that's another advantage. But those are all reasons why the Bahamas are great. But there are people do similar work all across the Caribbean, the Yucatan Peninsula, the Seychelles, Australia. So all along the kind of tropics, this kind of work done.
Awesome. Thank you for explaining that a little bit more. Cherry Ann was asking, do you have any activities or resources you recommend for classes that are interested in diving into this a little bit more?
I don't know. I actually haven't worked much with classes, and it's kind of sad that I don't see the students because I haven't worked much with like high school and middle school students. But there possibly is some material. I'd definitely be interested in following up and thinking more about what material might exist there.
Jackie, where was the first couple of slides that showed the sea level rise in New York? Is that something that's accessible?
Yes, thank you. Yeah, that's Climate Central. It says at the bottom of the slide. It has that they have amazing resources for kind of present day sea level rise risk. And you can actually, I teach a class on sea level change, and this is one of the assignments is to go on the website and you can look at different boroughs in New York City, how they will be affected. They also say how much property will be affected by how much sea level rise, and it's all sort of interactive. So that's a great resource. Yeah, that's a good point.
Awesome, thank you. Amberly was asking, so you mentioned a shark, running into a shark and running into a dog. Are there any other animals that you guys have run into while doing your research?
So we ran into goats a lot. I think they were wild. A lot of cancers. Is that what to call it? No, crabs. Sorry. So yeah, that was mainly it. Wasps as well. That was always the scare when we went kind of into the vegetation, that we would hit a wasp nest, and they don't like that. But there are not too many kind of big animals. So when you do field work anywhere that's remote, it can be a little scarce. So if you do field work around here in Canada, in more remote areas, you're afraid of bears or bigger animals that are actually harmful. Luckily, the most harmful was wasps, I would say, probably.
Scary. Awesome. Well, thank you so much for joining us today. Any other last little point or takeaway points you want to add?
I guess, for the students, if next time you're allowed outside and you're at a beach or at somewhere where there's a cliff, take a look at the rock and see if you can find some of these features, some of these layers in the rock maybe, and look a little closer.
Jackie,
thank you so much.
I actually have one last question related to that, being at the beach. So I'll do a show and tell in a second, but years ago, I found a piece of coral on a beach in Mexico, and I took it home. I've heard different things about taking rocks, taking coral from the beach. What are your thoughts on that?
Yeah, that's a good point, actually. I mean, I think if you find a loose piece of coral, I mean, I don't know the law, actually, I should say. If you find a loose piece on the beach, I think that's fine to take. When we take actual samples where we actually chip pieces out of the rock, we have a permit from the Bahamian government to do this research there. So that's definitely, and you saw us, it's destructive because you actually take little pieces of the rock. at that stage, you definitely want to have more sort of a permit, but if it's kind of loose, the next storm comes through, that all gets washed away. So I think there's enough dynamics in the system that that's okay.
Great. Well, thank you again so much for joining us. I think we all learned a lot today. I think I'm also going to be heading to the Bahamas to pick up that puppy, that poor little guy or girl. And we'll leave the shark to Meredith McDermott. She's the director of our office. She's our resident shark expert.
Awesome.
But thank you everybody for joining us, and big thank you to all three of our presenters today. Thank them in the beginning, but want to bring up their names again: Eliza Brenman and Lisa Williams, who helped put this event on. They spent a lot of time preparing, doing practice sessions. Also like to thank our Office of Sustainability staff who help us with those tests, who help us with the communications, all of those things. We really encourage you to keep the conversation alive. One of the ways we can do that is through social media, including Instagram. I'm going to talk a little bit more about one of our Instagram projects happening right now. If you weren't able to see the whole presentation, we will be sending out a recording after the fact and a PDF of the PowerPoint slides. We also have a couple other events coming up. So we have our next Meet the Experts session is on Friday, May 29th, same time, 1 to 3 p.m. And we're going to be talking about birds in the Arctic, volcanoes, and drone technology. So it's going to be another one of events where we have a lot of cool footage. So definitely stay tuned for that. You can sign up for that now on our Eventbrite page, which is at the bottom of your screen. Okay, so I mentioned our sustainability challenge on Instagram. This is a 10-day challenge where we encourage you to post a photo every day related to a specific sustainability action. So saving tap water, going meatless. Definitely check that out. Our Instagram is getting more and more robust, so we'd love to have you join the conversation. Our Instagram handle is at NYC School Sustainability. And another event that we have coming up, another digital event, we are having our future presentation on May 28th. This is a concert series with students, high school students, who are going to be performing songs related to sustainability. So they've been preparing for this all year. We're really excited that we're able to offer it digitally. It was originally an in-person event. It's going to be on May 28th at 6 p.m. And we're really excited because we're going to have Shutezcott Martinez join us. He is going to be hosting the event. He's an environmental activist and a hip hop artist. So he's going to be hosting, but also performing. And want to shout out my colleagues, Christina Langoni and Michelle Hudlin, who've put in a ton of work to Our Future event. I think one of the great things that's come out of this remote learning is we can open these events that may have had maximum capacity, being an in-person event. Anybody can attend this event, and we actually encourage you to invite your families to participate. And that's going to wrap things up for today. So thank you all so much for joining us.
Thank you, everyone. Have a wonderful weekend.
Thank you. Bye.